Hi everybody, this video is going to be on 11.3, the integral test. So to give a little background here, usually it is very hard or impossible to find the exact sum of a convergent series. Okay, so I'm going to say that this is usually only possible if our series is geometric or telescoping. Okay, so what we're going to do then is come up with some tests. So for this section through 11.7, we will develop tests that will help us determine whether a series converges or diverges. Okay, note we will not be able to say what it converges to, just that it converges. So this is an important distinction, okay? What I'm trying to say is that when we do these tests, the test will simply tell us if a series converges or diverges. Unfortunately, we're not going to know what the series converges to if it does converge. We're just going to know that it does converge to something. Okay? All right, so let me give a definition. So in 11.3 and 11.4, we're going to be talking about positive series only. So let me go ahead and write down one little definition here. So definition, we know what it means for a sequence to be decreasing, but what I want to say is f is eventually, and let me use the word ultimately instead. F is ultimately decreasing if there exists a capital N such that f is decreasing on capital N to infinity. Now, what am I trying to say here? I'm saying that, we don't care what something does in the short term. So, for example, it may start to go up and then back down. But all we care about is that from some point on, it is decreasing. So this would be an example of our capital N. So what we're saying is that from capital N to the right, we notice that the pattern is going downward. So we only care about what happens in the long run. Okay? All right, so let's go ahead and write down our theorem, our test. So theorem. This theorem is called the integral test. Which I'm going to abbreviate IT. Okay, so here are the conditions. Let's suppose that f of x is a continuous, let me just say, is a function that is continuous, positive, and ultimately decreasing. And all of this is on 1 to infinity. And let's let an equal f of n for all n that are natural numbers. Then this integral and this series behave the same. Now, what do I mean by behave the same? I'm going to be saying that a lot in this chapter. Behave the same means that they either both converge or both diverge. So let me just underline this part right here. So I'm going to say this guy and this guy both converge or both diverge. Okay. Now, what we are saying here is that we can tell what is happening with a series if we look at this integral instead. And we know how to take that integral, right? That's something that we practiced in chapter 7. So the idea is, if we know how to solve the improper integral there, if we get that this guy converges, then that means the series does also. And if we get that the integral diverges, then the series does as well. Okay, but we do have to state or show all three of these conditions, that it's continuous, positive, and ultimately decreasing. Okay. All right, let's do some examples here. Whenever you use a test, make sure that you state the test that you're using so that whoever's reading your paper, namely me, so that I could tell that your reasoning is correct, okay? And don't just guess and say it's converging or diverging. You have to show all of your steps. So let's go ahead and do an example. I'm going to do example 1. I'm going to say study the series. Okay, so this is my series I'm looking at. I'm looking at the series, the summation from n equals 1 to infinity of 1 over the square root of n plus 4. So because we are learning how to use the integral test, that's the test that we're going to use here. By the way, I want to show you guys the divergence test fails, because that would be the obvious first thing to always try. So let's look at the divergence test. What's the limit as n goes to infinity of 1 over the square root of n plus 4? This is equal to 0, right? If you send n to infinity, this goes to 0, which means we get no info, right? The divergence test tells us nothing. So it's always worth trying that, but we notice that it does not help us for this series. Okay, so instead we're going to try the integral test. So let's let f of x be 1 over the square root of x plus 4. This is always how you begin the integral test, is you have to specify a function and let the function equal the series. Essentially, you're just replacing the n's with x's. You're connecting the dots, right? So before we take its integral, we need to show that this guy is continuous, positive, and ultimately decreasing, right? Well, we know immediately f is continuous and positive on 1 to infinity. Why? Because the denominator is positive, first of all, and second of all, we know it's continuous and positive on its domain. The denominator is a radical, which makes it always positive. We're dividing a positive by a positive, so this has to always be positive. But what about decreasing? This is always the trickier part. In this case, it's not that bad because of the nature of the function, right? We could see, well, the usual easy way to do it, or one way that always works, is to take a derivative, right? So what is f prime of x equal to? Well, the function is the same as x plus 4 to the negative 1/2. So if you take its derivative, you get negative 1/2 times x plus 4 to the negative 3/2. Okay, which is equal to negative 1 over 2 times x plus 4 to the 3/2. Now notice that this is always negative, isn't it? It's always negative because the bottom is positive and the top is negative. So this is less than 0 on 1 to infinity. In other words, this means that f is decreasing on 1 to infinity. So we didn't even need to analyze certain intervals because it's decreasing everywhere. So we met all three conditions, right? We have continuous, we have positive, and we have decreasing. So that means that we can apply the integral test. So I'm going to say we now use the integral test. So what's the integral test? I'm going to look at this integral instead. Right, which we learned how to do in section 7.8, right? So this is, by definition, remember we need to write this as a limit as t goes to infinity of the integral from 1 to t of 1 over the square root of x plus 4 dx. Okay. So what would this equal? Well, what's the integral of 1 over the square root of x plus 4 dx? Remember, this is exactly let me rewrite this. This is x plus 4 to the negative 1/2 dx. And so if I want to take its antiderivative, doesn't that become 2 times x plus 4 to the 1/2, and I'm going from 1 to t. So this becomes 2 2 square root of t plus 4 minus, if I plug in 1, I get 2 square root of 5. What happens when I take the limit as t goes to infinity? Well, this guy goes to infinity, so the whole thing equals infinity. And so what does that mean? This means the integral diverges. Now what? So we are actually done with the problem because if you recall, let me go back to the integral test to remind you. The integral test says that either both converge or both diverge. So that means because we just determined that the integral diverges, the series must diverge also. So this is how we write the answer. By the integral test, the series also diverges. Okay, so that is how you use the integral test to solve a problem. Okay, let's do another example. Number 2. So study the series. This one's going to be the following. The series from n equals 2 to infinity. 1 over n ln of n. Again, I want to show that if you try using the divergence test, well, let's see what happens. We're going to do the limit as n goes to infinity of 1 over n ln of n. And of course, the bottom is growing without bound, so this just equals 0. In other words, the test tells us nothing, right? No info. Okay? So again, always try the divergence test, but understand that most of the time it's not going to work. It's only there for the rare case that that limit does not equal 0, right? That's when we gain something from using it. Okay, so I'm going to start by getting my function. Let's let f of x be 1 over x ln of x. Okay? What is the domain? The domain of f is, well, the bottom can't be 0. In other words, from 1 to infinity is the domain. Okay, so we cannot include 1. And by the way, this is why our sum starts at 2. But I'll show you how we deal with that in a second. So, f, where is f positive? Let's go back here for a second, okay? Where is f positive? Well, the natural log, what does the natural log look like? The natural log of a function, as soon as we pass 1, the natural log becomes positive, right? Because the natural log of 1 is 0. So this means that after 1, ln of x is positive, and x is also positive, so f is positive. So f is positive. And of course, it is continuous as well, right? Because ln and x are both continuous. So f is positive and continuous on 1 to infinity. Now, what about decreasing? Let's look at the derivative. What is f prime of x equal to? I'm going to go ahead and use the quotient rule to take the derivative. Okay, f prime of x is equal to the derivative of the top is 0 times the bottom is 0 minus the top times the derivative of the bottom. The derivative of the bottom I'm going to use the product rule to do. So it's going to be 1 times ln x plus x times 1 over x. And that's going to be all over the bottom squared. So this is equal to negative 1 times ln of x plus 1 all over x ln x squared. Okay? Now, where is this thing negative, right? We want to know where the derivative is negative. Well, the bottom is always positive because it's being squared. What about ln of x plus 1? So ln of x plus 1, if we set that guy equal to 0, we get that ln of x equals negative 1, or take e to the power of both sides, we get x is equal to e to the negative 1. Okay, what that means is that if I were to draw this, all I really need to do is plug something in that's bigger than 1 over e. So how about the number 1? What's f prime of 1? If I plug that in, I actually get, I can't plug in f prime of 1 because then I would be dividing by 0. So actually, yeah, let me erase this a little bit. There is a better way. So yeah, sorry, let me back up here, okay? Yes, this is 1 over e. But then at 1, we've got a break. And so we need to look beyond that. So I'm just going to plug in 2. Notice that if you look at f prime of 2, you do get a negative, okay? Plug in 2 in there and you'll see that everything is positive, and then you have that negative 1. So this is what you get. What did we just show? That f is decreasing after 1. So this means f is decreasing on 1 to infinity. Now, what do we do about this? We've got positive, continuous, and decreasing, but we can't include the number 1. So what this means is that I could say the following. F is continuous, positive, and decreasing on 2 to infinity. I need a closed interval, so I just wrote 2 to infinity because we definitely showed that, right? We showed that it's all three of those things any place after 1. So I'm saying at 2 and beyond, it's like that, right? So we can now use the integral test. So I'm going to look at the integral from 2 to infinity of 1 over x ln of x dx. Okay? So what is this integral equal? Remember, this is equal to the limit as t goes to infinity of the integral from 2 to t of 1 over x ln x dx. What is this equal to? Let's do this integral separately, just so we can find our answer and then plug it in. I'm going to let u equal ln of x, and that means that du is 1 over x dx. And so this integral becomes 1 over u, which is ln of u, which is ln of x. So if we come back to here, this is the limit as t goes to infinity of ln of x. We're going from 2 to t. So this is equal to the limit as t goes to infinity of ln of t minus ln. Now, ln of 2 is positive, so I don't really need absolute values for this because it's already a positive number. But what do you get when you send t to infinity? Then this guy goes to infinity, doesn't it? So this whole thing is equal to infinity. So this means the integral diverges again. So by the integral test, this series also diverges. What we're going to do now is use the integral test to actually study a particular type of series. So this is our definition. A p-series is a series of the following form. Okay, so it's 1 over n to the p. Any series that looks like 1 over n to the p for some real number p, this is called a p-series. Now you'll notice p could be any real number. It does not have to be an integer. It could be a fraction. It could even be an irrational number. So let me give you some examples. So for example, this series, n to the negative 3, this guy is a p-series. What does p equal? Well, n to the negative 3 is the same as 1 over n to the third power, so it's a p-series with p equal to 3. Okay? Let's do another one just so we can make sure we understand. What about the series 1 over the cube root of n to the 5th? Now you'll notice that this does not necessarily look like a p-series, but it is one because I can write it this way. Right? This is 1 over n to the 5/3. So this guy is a p-series with p equal to 5/3. So question, what p-series converge and which ones diverge? Okay, let me show you something really quick here. One last one that you guys are well aware of. Recall the harmonic series? Remember this guy? This guy is a p-series with p equals 1. Remember, what we found out is that this series actually diverges. We proved that in the last section. So we ask a natural question. So question, which p-series converge and which ones diverge? Okay, we can imagine that it depends on the value of p, right? Because certain p's are going to make the series really small or really big, so it's probably going to change whether it converges or diverges. So it turns out we can use the integral test to solve this or to answer this question once and for all, and this will give us a nice tool that we're going to use from now on whenever we talk about p-series, okay? So this leads us to a theorem. The p-series okay, this p-series 1 over n to the p is convergent if p is bigger than 1 and divergent if p is less than or equal to 1. So it turns out that 1 is the cutoff. Okay? So I am going to do the proof of this, and I'm going to show you how we can use the integral test to prove that this is true, that 1 is the cutoff here. Okay, so let's do some cases here. First, case 1, what happens if p is a negative number? Well, I'm going to use the divergence test. What would be the limit as n goes to infinity of 1 over n to the p? Well, if p is a negative number, then this is the same as the limit as n goes to infinity of n to the negative p, right? But since p is a negative number, now this guy is positive, isn't it? And so what does this limit go to? It equals infinity, because infinity to the power of any positive number is infinity, which is not 0. So what does the divergence test tell us? It diverges. Okay, so we now know that for p is less than 0, it diverges. Okay, case 2. What about p equals 0? If p is exactly 0, then that means our series, if we plug in 0, we actually get, what's anything to the 0? It's 1. We're actually just adding this up. Okay? But we can use the divergence test again. What's the limit as n goes to infinity of 1? It's just 1, which is not 0. So this means it diverges. Okay, so we now know what happens when we're less than 0. We now know what happens when we're equal to 0. So now we're going to do case 3. P is greater than 0. Okay? So we're going to let f of x be 1 over x to the p. Remember, we're assuming that p is positive here, okay? What do we notice about f? Certainly, f is continuous, positive. Let me just say it's continuous and positive on 1 to infinity. That's obvious, right? Because this thing is clearly defined on 1 to infinity. There's no discontinuities after 1. And it's positive because we're only plugging in positive x's from 1 to infinity. And a positive number to a positive power is, of course, positive. Okay. What about the derivative? This is just x to the negative p, right? This is x to the negative p. Its derivative is negative p over x to the negative p minus 1, or p plus 1 down here. Okay. Bottom is always positive though, so this guy is less than 0, which means that f is decreasing on 1 to infinity. Okay, so this means that we can just look at the integral test. So the integral test applies. So I'm going to look at the integral. We're going from 1 to infinity. Let's see what we get here. We know that this is the limit as t goes to infinity of 1 to t, and we're integrating x to the negative p dx. So let me go ahead and do this integral. So if we do this integral, taking this integral, it actually depends on what p is, because p could be 1 or it could be -1, right? Sorry, p could be 1 or it could be any other number. So what if p is, let's do the p equals 1 case first. This means that we're doing the limit as t goes to infinity of the integral from 1 to t of x to the -1 dx, which is equal to the limit as t goes to infinity of, what's the antiderivative of x to the -1? It's ln of x, right? So it's ln of x going from 1 to t. So this is equal to the limit as t goes to infinity of ln of t minus ln of 1, which is 0, which is just infinity. So this means it diverges, right? So now let's do p is not 1. What's the limit as t goes to infinity of the integral of 1 to t of x to the -p dx? Well, we can now use the power rule on this. We get the limit as t goes to infinity of x to the -p plus 1 over -p plus 1, and we're going from 1 to t, which is equal to the limit as t goes to infinity of t to the -p plus 1 over -p plus 1 minus, and if you plug in 1, you get 1 over -p plus 1. So what does this integral equal? Well, 1 seems to be the cutoff here, right? So what if p is between 0 and 1? If p is between 0 and 1, then this means that this guy is a positive power, right? So what we get above is equal to the limit. Let me write it this way so you guys could see what I'm talking about. I get t to the 1 minus p, right? Because -p plus 1 is the same as 1 minus p over 1 minus p minus 1 over 1 minus p. But if you send t to infinity, infinity to a positive power is infinity. Okay? So what does that mean? Okay, this guy goes to infinity, so the answer is infinity. In other words, it diverges. Okay? If we go back a step 2, we notice we got diverges also. So we've now determined that we diverge. We diverge if we're less than 0. We diverge if we're equal to 0. We diverge if we're between 0 and 1. We diverge if we're at 1, but now comes the moment of truth. We're going to see what happens when we're bigger than 1. So if p is larger than 1, then this actually means that -p plus 1 or 1 minus p is actually a negative power, right? So I can actually write this as follows. I flipped it to the other side. Okay? Because now p minus 1 is positive, and so if you send t to infinity, this guy actually goes to 0. So this limit actually exists. It's -1 over 1 minus p. In other words, the integral converges. So the only case where it converges was when p is larger than 1. So that finishes the theorem. Okay, so I know that we went through that proof and it was a lot of steps, but let's go back so we can understand the theorem. The theorem is very simple. Okay, this is what you need to remember. It's saying that when you have a p-series, then it's convergent if p is larger than 1 and divergent if p is less than or equal to 1. Okay, you don't need to go through that whole proof. All you need to do is tell me what p is and then what you can conclude. Okay, that's all there is to it. Okay, so let's do a quick example here. I think we're on example 3. And we're just going to practice using this p-series test. So study the series. A summation from n equals 1 to infinity of 1 over n squared. So we want to determine whether this thing converges or not. So what do we notice? We notice that this is a p-series with p equal to 2, which is larger than 1. So this means the series converges. Right? It's that simple. Let's do another one. Study the series. We're adding from n equals 1 to infinity of 1 over the cube root of n. Now notice that this series is the same as 1 over n to the 1/3. So this guy is a p-series with p equal to 1/3, which is less than or equal to 1. This means the series diverges. Okay? This is a really useful tool. Okay, this tool is really useful because we end up with p-series all the time when we're using tests, especially when we use the comparison test, as you'll see in the next section. So make sure that you get the p-series down pat because it's going to be extremely helpful for the rest of the chapter. Okay, guys, that concludes this section. Thank you very much for watching.